in our introduction to magnetism. Here are the syllabus goals that we have today for IV. We want to be able to state that moving charges give rise to magnetic fields. We should be able to draw magnetic fields around, or magnetic field patterns that are created due to currents, and define the magnitude and direction of a magnetic field. Okay, so we've been doing electricity, and now we're getting into magnetism because they are closely related. When we talk about the four fundamental forces of the universe, one of those four fundamental forces is electromagnetism. So electricity and magnetism have this relationship. The relationship between electricity and magnetism was discovered in the 1800s. Okay, but magnetism itself has been around and has been recognized for thousands of years. As long as 2,000 years ago, folks in ancient Greece and that part of the world discovered rocks that had weird properties. They would stick together, things would stick to them, they would do weird stuff. Those rocks were first located in a region of the world that we called Magnesia, and that's why we still call them magnets today. And we talk about magnetism because that part of the world is where it first came from. And magnets have been used for a long time for a variety of things. The Chinese, as far as we know, were one of the first cultures to recognize that you could take these magnetic rocks, these weird rocks, you could take a piece of them and either float them in some kind of oil or hang them by a string, and they would align themselves north and south. They created the first compass using a magnet. And this was like in the 1100s. Okay, we're a long time ago. Today we use magnets for all sorts of things. Any device that has an electric motor deals with magnetism. Okay, if you have a Prius car, an electric car, if you have a blender, if you have a vacuum cleaner, anything that uses a motor and electricity is dealing with magnetism. We use magnetism to generate almost all of the electricity that we use. So whenever you plug something into an outlet, magnetism is involved in that process, and that's one of the reasons why it's important for us to figure out how it works. Now, you guys have probably been playing with magnets before in your life. You've seen them, you've messed around with them. What do magnets do?
Stick together and repel.
Okay, and in terms of physics, what is that called? Attraction or repelling. And what's the word that defines something attracting or repelling or pushing or pulling? What? Force. They exert forces, right? Magnets exert forces. Now, do magnets exert forces on everything? No. What do they exert forces on? Other magnets or metal. All metal? Okay. Well, you guys are thinking superatomic, but let's don't think superatomic right now. Let's just think kind of generally. What kind of metals are magnets attracted to? Iron. Iron. Aluminum? No. Copper? No. Stuff that has iron in it, like steel. Okay. So magnets exert forces on, magnets exert forces on other magnets or on objects that have iron in them. Okay, those tend to be the things. They are discovering other magnetic materials today, but generally those are the main ones. Do magnets have to be touching one another to exert a force? No, they don't. Magnets exert forces over distances. Great. And you guys said it earlier, do they only exert force in one direction? No, because sometimes they attract, sometimes they repel. Great. Now that's different than gravity, right? Gravity only attracts. But electricity is also attractive or repulsive. Remember, we had positive, similar charges repel and opposite charges attract when we talk about electricity. Magnetism is very similar. Yeah. So with electric charge, we talked about positive and negative charges. What do we talk about with magnets? Poles. We talk about poles, but do we call them positive and negative? North and south. Okay, so with magnets, we talk about them having poles. Rather than electric charges, we have a positive charge and a negative charge. With magnets, we have a north pole and a south pole. Okay, so they have polarity. North and south pole is what we've decided to name them. There's no specific reason why we did that, except for maybe the Earth's magnetic field had something to do with that. But here's a weird thing about magnetic poles. If I have a magnet that has a north and south pole, and I break it in half so that I can have a north pole and a south pole, I can't do that. When I break it in half, the two pieces will each have north and south poles. And if I break those in half, those little pieces will have north and south poles. All the way down to the atomic level, I can break it and break it and break it. I will get a north and south magnetic pole. They come in pairs. You can't isolate them on a particular magnet, okay? Which is kind of weird because there is certain theories that show that there should be magnetic monopoles. There should be isolated magnetic poles, theoretically, but for some reason, it just doesn't seem to happen. We can't see. It's never been discovered. Okay. Just like electricity, with magnetism, if I put opposite poles together, they'll be attracted, and if I put similar poles together, they'll be repelled. Okay. Electricity, that was true for charges. Magnetism, that's true for polarity. Let's look at some pictures. Let's look at some pictures. Look at that. Okay, here's some magnets. Notice that each of these magnets has two poles, north and south. If I bring the north poles together, those magnets will be repelled. If I bring the south poles together, they'll be repelled. And if I bring opposites together, they'll be attracted. It's awesome. Opposites attract, just like in life, okay? And here's that thing I was talking about, how you can't isolate those poles. I take the bar magnet and I break it in half, I get new north and south poles. And I break those in half, I get new north and south poles. And that would happen all the way down to literally, it would happen on an atomic level. It's kind of bizarre that way. All right. We've talked about gravitational fields. We've talked about electric fields. We're going to talk about magnetic fields, okay? One of the ways to describe the forces that magnets exert is by thinking of them as having a force field or a magnetic field, okay? And the magnetic field is going to be represented by the letter capital B. So in an equation, when you see capital B, you should be thinking magnetic field, magnetic field. And just like gravitational and electric fields, we will represent magnetic fields using lines, but more specifically, we won't really use lines. You should be thinking about using arrows. Because remember, there will be lines with direction. They will have a definite direction. And we've defined the direction of the magnetic field as the direction that is indicated by the north needle on a compass. So when I take a compass, which basically is a little magnet, and I place it in a field, it will align itself so that the north end of that compass needle points the direction of the field at that location. All right? And that is why, since opposites attract, think about when your compass, when you're out in the woods, it's aligning with the Earth's magnetic field. The north needle is pointing to the south magnetic pole, which is in the north. Go figure, okay? So the Earth's south magnetic pole is in the northern hemisphere, and the Earth's north magnetic pole is in the southern hemisphere currently. It switches. It switches on geologic timescales. Our magnetic pole flips, and sometimes the north magnetic pole is in the north, sometimes it's in the south. We happen to live in an era when the north magnetic pole is in the southern hemisphere.
Kind of like one day bam.
Great question. Okay. How it flips, and this is something I want to talk about a little bit later in the PowerPoint. How it flips is unknown, because the only reason we know this happens is because of the geologic record. And so on a geologic time scale, we know that it flips really quickly. But a quick geologic time scale could be 1,000 years or 100 years. But it also could happen in a week. And we don't have evidence specifically to know how quickly it flips. But I want to talk about it a little bit more later in the PowerPoint. And you guys, when we're drawing magnetic field lines, again, it's just like electric field lines. The concentration will determine the strength. If the field lines are curved and we want to know the direction of the field at a specific location, it would be a tangent, a straight line that touches that curve at that point. That would be the direction of the field at that point. The concentration of the lines tells you how strong the field is. So if the lines are closer together, you have a stronger field. If the lines are farther apart, you have a weaker field. Okay? Very, very similar to gravitational fields and electric fields, right? Electric fields, what direction do the lines go? From what to what? From positive to negative. Magnetic fields, what direction do the lines go? From what to what? Well, we don't, in the magnetism, we talk about north and south. So is it from north to south? Because remember, the compass needle, the north needle of the compass, will be attracted to the south magnetic pole and repelled from the north magnetic pole, and that's the direction of the field, from north to south. Okay? That's how we draw the field lines. So visually, this is what it kind of looks like. If I took a bar magnet, which has a north and south pole, and I placed a compass around it, the needle would change the direction that it points depending on where I am. And it always would point away from the north pole and ultimately towards the South Pole. And then if I did this a lot, this is the magnetic field that I would see. And notice that the field lines are going away from the North Pole and towards the South Pole. Notice also that the magnetic field is much stronger here than it is over here because the lines are much closer together. Nick. Okay. And the other thing to think about this, you guys, is we draw this, we're always drawing two-dimensionally, but we live in a 3 or 4-dimensional world, or if you believe string theory, a 9 or 11-dimensional world. But my point being that this is two-dimensional, but really it's three-dimensional. You know what I mean? So you got to kind of imagine it as actually being more like a, I don't know, a copepod or something. One little, you know what I mean? Those little things. You know, right? Where those? Okay, so here's what the field looks like around a regular bar magnet. There's a few field patterns that IB expects you to know. I think that was one of the syllabus things we talked about at the beginning, like be able to draw the field lines around certain things. You should know that, okay? If I brought two similar magnetic poles together, what do you think it would look like? Just like similar charged particles, right? Excellent. Okay, but these are opposite. If I brought two opposite charged poles together, it would again be like opposite charged particles. Notice that you get that nice uniform field, and then you get a little bit of the edge effect. And then if I brought similar poles together, just like you guys just said, it would be more like that, where the field lines would go apart. You'd have a point there in the middle where there would be zero magnetic field. You'd have some sort of equilibrium point. So again, the Earth does have a magnetic field, and it's like the Earth it's as if the Earth has a giant bar magnet inside of it. That's kind of what the Earth's magnetic field is like. This is why compasses work, because they align themselves with the magnetic field lines. And if you have a really fancy schmancy compass, not only does it move in the horizontal plane, but it can tilt vertically. And you can measure the angle that the magnetic field is actually tilting into the Earth or coming out of the Earth. So notice, if you went up here more, your compass needle would point down into the Earth, because that's what the field is doing there. And if you're right down here at the equator, it would be perfectly horizontal, and it could show you the tilt as well. Now, there's a while, in geology, particularly in igneous rocks that form from molten magma, when the magma cools and solidifies, there's certain minerals in those rocks that will align themselves with the Earth's magnetic field. And because of this, geologists have been able to measure what the magnetic field of the Earth has been like over the course of the geologic record that we have in the rocks. Particularly on the ocean floors have been a good place to notice this. The Atlantic Ocean was the first place we found a really good mapping of the Earth's magnetic field. And what they did notice is that the magnetic field flips. Sometimes the north magnetic pole is in the north, and sometimes it's in the south. Right now, it's in the north magnetic pole is in the south. It appears that we're overdue for a flipping. Okay, again, it doesn't happen on a very regular interval. Sometimes it lasts longer, and sometimes it lasts shorter. But we are beyond the average period where the magnetic pole has stayed one direction. So we're in it, and there is evidence that the magnetic field is weakening. There are people studying this stuff, and it does appear that the magnetic field is weakening, and that we might be up for a flip. We don't, hang on a second, I know you guys have questions, but let me go through this thought process for a second. We don't know how quickly it flips because the geologic time scale, we know it does it quickly on a geologic time scale, but on a human time scale, we don't know. Why is this important, and why does this matter? Well, I hope I have this picture next. Look at that. This is the picture, okay? The magnetic field of the Earth is like a nice little safety bubble. It is a force field that protects us from the harsh charged particles of space that we call the solar wind, and sometimes we call them cosmic rays. The sun is spewing out all sorts of material into space at near the speed of light, and it would be dangerous for us. It would cause mutations and possibly death if you were exposed to the solar wind fully without any protection, without the atmosphere, without the magnetic field. One of the things we're going to learn about next class is that if I have a charged particle moving in a magnetic field, there'll be a force exerted. It'll deflect that particle. And so much of the solar wind gets deflected by the Earth's magnetic field. Some of it, however, notice that we have these poles, right? Some of these particles actually get trapped and spiral down either the North Pole or the South Pole. And when they do that, they interact with the Earth's upper atmosphere, exciting the molecules, causing them to glow. And that's what creates the northern lights and the southern lights. If we lose the magnetic field, there will be lots of aurora, yes. But there's also something else to consider. And I think this is something that I read one time a long time ago. And I don't know if it's a prevalent theory, but it's a pretty cool theory. And one theory is this. When we look at evolution, when we look at the fossil record of how animals and organisms have evolved on Earth, there are two main theories of how that change happens. One is called gradualism, that just as time progresses, things just kind of change. But the other theory, and it's heavily supported in the fossil record, is that evolution happens in more what are called fits and starts. Like you have this period of stasis where things don't change very much, and then you have this period of rapid evolutionary change. And there is evidence in the fossil record that evolution happens this way. It's called the theory is called punctuated equilibrium. You'd have rapid change and then stasis, and then rapid change and stasis, and then rapid change. There are some people that have come up with an idea, and again, I haven't investigated deeply enough to see if this has been purely verified or not, but one theory is that these periods of rapid evolutionary change in the fossil record coincide with times in the Earth when the magnetic field was flipping. And if there was a period with no magnetic field, there would be more radiation coming from space, which potentially would cause more genetic mutation, which potentially would cause more rapid evolution. And then when the magnetic field builds itself back up and protects us, we have a period of time where things don't change so much. Evolution slows down for a while. So again, I don't know that that's necessarily an accepted theory in all the world of evolution and astrophysics, but it was kind of a cool idea. Now let's talk about electricity and magnetism kind of combined here. In 1820, there was a scientist by the name of Hans Christian Ørsted who did a kind of earth-shattering experiment, or he made an earth-shattering discovery about electricity and magnetism. I'm going to do that for you here so you can see how profound. So by putting current through a wire, when Ørsted discovered that the compass needle moved, what did he actually discover? What was he showing?
They're connected.
Electromagnetism. What does a current carrying wire create? What kind of a field? Well, remember, a compass is a magnet. It creates a magnetic field. Okay, that was what Ørsted discovered, that a compass, a current carrying wire, creates a magnetic field. And he explored it even further and discovered that the shape of the magnetic field around the wire is circular. It creates a circular magnetic field around a wire when you have electricity flowing through that wire. Now again, this may not seem like much of a discovery, but it is the foundation for civilization as we know it today. Ponder that for a little while. And now the question is, if it creates a magnetic field in a circle, what direction is it going? Because remember, magnetic fields have direction. So we come up with our first right-hand rule. You're going to learn 3 or 4 right-hand rules with electricity and magnetism. This is the first one. And in order to do the right-hand rule correctly, you must raise your right hand. If you do the right-hand rule with your left hand, you will get these wrong on tests, okay? So remember, if you're right-handed and you're writing on a test and you have a question where you have to do the right-hand rule, put your pen down and use your right hand. Because if you keep writing and use your left hand, it won't work, okay? Okay, here's the first right-hand rule. If I have a wire with current in it, and I grab that wire with my right hand so that my thumb points the direction of the conventional current. Now, what direction is conventional current in a circuit? From positive to negative, okay? Remember, we know electrons go the other way, but we draw current from positive to negative. If I grab the wire with my thumb pointing the direction of the conventional current, then my fingers would wrap around that wire in the direction of the field. That's the first right-hand rule, okay? Grip the wire with the right hand such that your thumb is the direction of the conventional current. Your fingers will curl around that wire in the direction of the magnetic field. Let's look at this right-hand rule here for a second. All right? This is it. It's pretty simple. If I have a current-carrying wire, I grab it with my right hand so that my thumb is aligned with the conventional current, and my fingers will wrap around the wire in the direction of the magnetic field. Notice that the field is stronger close to the wire, weaker as you get farther away from the wire, but it's just in a circular pattern around the wire. Okay? Now imagine what would happen if instead of a straight wire, I had a loop of wire. What if I made a loop of wire so the current, take that right-hand rule and see if you can figure out what's going on. What would it look like? Okay? Something like that, right? Something like that. Notice if I had more than one loop, and we'll talk about this more later, if I had more than one loop, all of a sudden I'm starting to generate a magnetic field that looks like a bar magnet. Would this right-hand side be the north or the south pole of that bar magnet? North. Remember, the magnetic field lines go away from north and towards the south. Okay? This is one way you can create a magnet just using electricity. We call them electromagnets. If you have a coil of wires and you run current through them, you will create a magnetic field that is just like having a magnet. Turn off the current, no more magnet. Turn on the current, magnet. Really nice for making really precise switches. Really nice for making things like those big cranes that you see at junkyards. They like pick up the cars. You ever seen that? You know, they pick up the cars and they move them around and then they drop the cars. They're using magnets, electromagnets. They can turn that magnet on and off with electricity. We'll talk more about that later. So let's think about this for a second. If an electric current creates a magnetic field, what exactly is an electric current? No, what? Let's think back to electricity. What is electric current?
Flow of electrons.
Flow of electrons. And electrons are charged particles, right? So it appears that moving charged particles generate magnetic fields. And it turns out that that is true. Moving charged particles generate magnetic fields. And that's kind of the main connection there. Moving electric charges, whether they be protons or electrons, but we usually talk about electrons in a wire, cause a magnetic field. Now let's think about this for a second. You're made up of atoms, right?
Sure.
And everything. Everything's made up of atoms, right? We've got a nucleus with protons and neutrons. Is the nucleus moving very much?
No.
No. But what's going around that nucleus?
Electrons.
Are they moving?
Yes.
So every atom in your body is generating a magnetic field. Every atom in this table is generating a magnetic field. But why is it not magnetic?
Very weak.
Okay? It turns out that in most materials, let's imagine I just have a regular old piece of wood. It's not magnetic. I don't have stuff sticking to it. Every atom of that wood is creating a little magnetic field, but they're random in direction. Some are going this way, some are going this way, some are going that way. They're totally random, and the net result is that all those magnetic fields cancel themselves out. In a magnet that is a permanent magnet, like a piece of iron that is magnetized, something has happened to align all of those magnetic fields. And they're not perfect. There's usually one or two that are kind of off, but most of them are going the same direction, so that the net result is you have a stronger magnetic field, and that thing is magnetized. Now, you can align magnetic fields in different ways, okay? So what we were just talking about here, let's get rid of that, that, you know, electrons moving on an atomic level are basically what generate magnetic fields. Electrons are orbiting, but they're also spinning. In most materials, those individual little magnetic fields cancel out, but in iron and in magnetized substances, they have aligned, and then you generate a magnetism. Those little bitty magnetic fields, we tend to call them domains. They kind of work more, rather than on an individual atomic level. Usually it's like a region of an object. We call those domains. And current electricity is just moving electric charges, and that's why it generates a magnetic field. When you have current flowing, you have moving electric charges, and a magnetic field gets generated. All right.